You see a comet streaking across the night sky, beautiful, ancient, the tail streaming behind like hair in the wind. Except it is not behind. When the comet moves away from the sun, the tail goes first. The comet follows its own tail through space like a bizarre cosmic reversal. Why? Why does every single comet tail point away from the sun no matter which direction the comet travels? What force pushes millions of tons of ice and dust in one direction while ignoring the comet's momentum? And what does 3I Atlas, the interstellar visitor racing through our solar system right now in 2025, reveal about this phenomenon that confused astronomers for centuries? Johannes Kepler watches Halley's comet blaze across the sky. The tail stretches wide, arcing away from the sun. Kepler's mind races. Sunlight must be heating the comet, he thinks. But more than that, the sun's rays must be pushing the material away. He cannot prove it. No instruments exist to measure such tiny forces. But Kepler writes it down anyway in his book De Cometis Libelli Tres, published in 1619. A comet's tail is formed by matter that the sun's rays chase through their impulses outside the comet's body. 4 centuries before lasers would confirm radiation pressure in laboratories, Kepler guessed the answer by watching the sky. This script is researched and factual, using sources from the Keck Observatory's October 2025 spectroscopic analysis, published in their recent paper on 3I Atlas spatial profiles, and from the Gemini South Telescope observations, published by Neuralab in August through October 2025, showing the developing anti-solar tail with precise measurements at 56,400 kilometers in length. These are not press releases. These are the actual observation data from 8.2-meter telescopes capturing light that left an interstellar object millions of miles away. Now back to the information. Russian physicist Pyotr Lebedev walks into his Moscow laboratory in 1900. He suspends a tiny vane in a vacuum, shines light on it. The vane moves. Actually moves. Lebedev measures the pressure. 7 times 10 to the negative 6 newtons per square meter. Microscopic, but real. That same year, American physicists Ernest Fox Nichols and Gordon Ferry Hull repeat the experiment at Dartmouth College. Same result. Light carries momentum. Photons streaming from any source hit any surface and transfer momentum. Newton's third law applies even to particles with no rest mass. When a photon moving at the speed of light hits a dust grain, the grain must move to conserve momentum. The mathematics work out simply. A photon with frequency omega has momentum equal to h bar omega divided by c. For 1 watt of light power hitting a perfectly reflecting surface, the force equals roughly 10 to the negative 9 newtons. Seems like nothing. But in space, nothing else pushes back. No air resistance, no friction. That microscopic force becomes the dominant force acting on small particles. Now we know light pushes. But comets have 2 tails, not 1. The dust tail curves gently. The ion tail points lasers straight away from the sun. Different mechanisms, different physics, both pointing away but behaving differently. The dust tail forms when sunlight heats the nucleus. Water ice, carbon dioxide ice, carbon monoxide ice sublimate directly from solid to gas without melting. The escaping gas carries dust particles with it. Once free, radiation pressure takes over. Photons from the sun strike dust grains continuously. Each impact transfers momentum. Grains smaller than 0.006 centimeters get pushed away faster than gravity pulls them back. Larger grains stay closer to the comet's orbit, forming the curved dust trail. The curvature happens because dust particles retain some of the comet's orbital velocity, while radiation pressure pushes them outward. They move in their own orbits around the sun, gradually diverging from the parent comet. The result is a broad, curved, relatively featureless tail that can stretch tens of millions of kilometers. UV photons knock electrons off the molecules. Ionization. The molecules become electrically charged. Now the solar wind enters the picture. The sun does not just emit light. It emits a continuous stream of charged particles. Protons and electrons mostly, racing outward at 400 kilometers per second in the inner solar system. This solar wind carries the sun's magnetic field with it, the interplanetary magnetic field. When the solar wind encounters the ionized gas from the comet, electromagnetic forces dominate. The cometary ions get picked up by the solar wind's magnetic field. Magnetic field lines drape around the comet, forming a cometary magnetosphere. The ions stream along these field lines, creating a straight ion tail pointing radially away from the sun. This tail glows blue from fluorescence when CO plus ions absorb sunlight and re-emit at 4,200 angstroms wavelength. The ion tail stays narrow and straight because magnetic forces are far more effective at containing ions than radiation pressure is at pushing dust. The tail points precisely away from the sun, following the solar wind's flow direction. Pre-discovery observations stretch back to June 14th from multiple Atlas telescopes worldwide and from Caltech's Zwicky Transient Facility, an interstellar object. The third confirmed visitor from beyond our solar system after 1 Oumuamua in 2017 and 2 Borisov in 2019. But 3 Atlas behaves strangely from the start. By July 21st, Hubble captures images showing a teardrop-shaped cocoon of dust around the nucleus at a distance of 277 million miles from Earth. The comet sits beyond Jupiter's orbit. That distance at 2.33 astronomical units from the Sun normally keeps comets frozen and inactive. Solar system comets usually wait until they pass inside Jupiter's orbit before their ices start sublimating enough to form visible tails. Not 3I Atlas, it starts out gassing early. Way early. Only 6.6 kilograms per second of water, 14 kilograms per second of carbon monoxide. The water output equals just 5% of the carbon dioxide output. Normal solar system comets are dominated by water ice. 3I Atlas is the opposite. 87% carbon dioxide, 9% carbon monoxide, only 4% water by composition. Carbon dioxide ice sublimes at much lower temperatures than water ice, at negative 78.5 degrees Celsius compared to 0 degrees Celsius for water. This allows 3I Atlas to become active much farther from the Sun than water-rich comets. The interstellar object's unusual composition tells us it formed in a very cold region of its home star system, far beyond that star's frost line where CO2 could freeze solid. NASA's SphereX mission maps the CO2 plume between August 8th and 12th. The carbon dioxide cloud extends 348,000 kilometers from the nucleus, a teardrop shape. Harvard physicist Avi Loeb calculates on the morning of August 27th that the outer edge of this plume occurs exactly where the ram pressure of the solar wind equals the ram pressure of the CO2 outflow. The solar wind pushes inward at 400 kilometers per second. The carbon dioxide gas pushes outward. Where these pressures balance, the plume's edge forms. Inside this boundary, cometary gas dominates. Outside, solar wind dominates. The boundary creates the teardrop shape, with the narrow end pointing toward the Sun and the wide end streaming away. August 27th. The 8.2-meter Gemini South telescope on Cerro Pachon in Chile uses the Gemini multi-object spectrograph to capture deep multiband images of 3I Atlas. The observations reveal what no one expected. An anti-solar tail stretching 56,400 kilometers pointing southeast directly away from the Sun. The surrounding coma measures 18,800 kilometers wide, much larger than observations from just weeks earlier in July. This is the classic cometary configuration. Heat from the Sun causes outgassing. Radiation pressure and solar wind shape the emitted material into tails pointing away from the Sun. Except 3I Atlas is not a normal comet. Its trajectory is interstellar, its composition is bizarre, its behavior defies standard models. The cyanide coma stretches 180,000 kilometers across on September 15th, asymmetric and elongated along the anti-solar direction. A visible dust tail extends 50 arcseconds, corresponding to about 100,000 kilometers. The comet has an apparent magnitude of 14.2, bright enough for large telescopes, but too faint for the naked eye. As 3I Atlas approaches perihelion, the closest point to the Sun, activity increases dramatically. More heat means more sublimation, means more gas, and dust streaming away means longer, brighter tails. Europe's ExoMars. Trace Gas Orbiter images the coma with its color and stereo surface imaging system. These spacecraft observe 3I Atlas from angles impossible from Earth, providing stereoscopic views of the developing tail structure. The comet appears 50,000 times fainter than what the orbiter usually images, requiring 5-second exposures. The Keck Cosmic Web Imager spectrograph examines wavelengths from 0.3425 to 0.55 micrometers. The data, published in October 2025 by Willem Hugendam and colleagues, reveals something bizarre: clear detection of nickel and cyanide in the outgassing plume. Weak or no detection of iron. Natural comets always show iron and nickel together because both elements form simultaneously in supernova explosions. They travel together through space. They condense together in protoplanetary disks. Finding nickel without iron resembles finding industrial alloy production more than natural cosmic chemistry. The nickel emission concentrates in the innermost 2,000 kilometers of 3I Atlas. The cyanide extends farther out to 841 kilometers. The spatial profiles suggest nickel might be released by an intermediate parent molecule quickly broken apart by solar radiation. Perhaps nickel attached to polycyclic aromatic hydrocarbons, forming molecules like nickel naphthalene. The tail still points away from the sun because radiation pressure and solar wind still operate the same way regardless of chemical composition. The dust particles, whether they contain iron or nickel or neither, still get hit by photons, still experience momentum transfer, still get pushed away from the sun. The ions, whether they are CO plus or CN or nickel ions, still get picked up by the solar wind's magnetic field, still stream along field lines pointing radially outward. The mechanisms Johannes Kepler guessed at in 1619 still govern the behavior of an interstellar comet from another star system 4 centuries later. 130 million miles, just inside Mars's orbit. The surface temperature increases dramatically. Outgassing accelerates. The stress environment increases. As Avi Loeb writes, a high-stress environment elicits confessions. The comet reveals its nature through its response to solar heating. The tail grows more prominent, more visible. The geometry changes as Earth's viewing angle shifts. What was a foreshortened tail hidden behind the coma in July becomes a spectacular display stretching across the sky in October and November. The comet becomes visible in the pre-dawn sky for observers in the southern hemisphere, not naked eye visible but accessible to amateur telescopes. The European Space Agency's Hera spacecraft potentially passes through 3I Atlas's ion tail. The spacecraft's instruments might detect signatures of an interstellar comet's plasma, characteristic changes in the solar wind, a magnetic draping structure associated with the comet. From October 30th to November 6th, NASA's Europa Clipper on its way to Jupiter also potentially traverses the ion tail. 2 spacecraft, 2 chances to directly sample an interstellar object's tail, to measure its composition, to test theories about how cometary ions interact with the solar wind, to understand what an object from another star system carries with it. Radiation pressure depends only on the intensity of light and the cross-sectional area and reflectivity of the particles being pushed. It does not matter if those particles originated around our sun or another star 100 light-years away. The formula is simple. Pressure equals intensity divided by the speed of light for absorbed radiation. Pressure equals twice intensity divided by c for reflected radiation. For sunlight at Earth's distance, intensity is about 1,360 watts per square meter. The radiation pressure is about 4.5 times 10 to the negative 6 pascals. Tiny. But acting continuously on dust grains with masses measured in nanograms, this pressure produces noticeable acceleration. A grain, 1 micrometer in diameter with density 1 gram per cubic centimeter, experiences acceleration of several meters per second, squared from solar radiation pressure at 1 astronomical unit. Over hours and days, this adds up to significant velocity changes. The solar wind mechanism also does not care about origin. The solar wind at 1 astronomical unit has a density of about 5 protons per cubic centimeter, traveling at 400 kilometers per second. When these protons encounter freshly ionized cometary gas, electromagnetic interactions dominate. The newborn ions, called pickup ions, get swept up by the solar wind's magnetic field. The magnetic field lines drape around the obstacle created by the comet and its coma. This draping process is well understood from decades of spacecraft observations at comets Giacobini-Zinner in 1985, Halley in 1986, Griggs-Skellerup in 1992, Borrelli in 2001, and most recently Comet 67P Churyumov-Gerasimenko by the Rosetta spacecraft from 2014 to 2016. The physics is universal. Solar wind plus ionized cometary gas equals plasma, tail pointing away from the sun. This is not a tail pointing toward the sun, despite the name. An anti-tail is an optical effect. Large dust particles ejected from the comet nucleus are too heavy for radiation pressure to push away efficiently. They remain roughly in the comet's orbital plane, forming a disk of particles along the comet's orbit. When Earth passes through or near this orbital plane, we see the disk edge on. It appears as a spike or spike pointing toward the sun because we see particles on both sides of the comet's orbit stretching into the distance. The anti-tail of 3I Atlas was first observed by Hubble in July 2025, pointing eastward. By late August, Gemini South observations show it had grown and become more visible. Notable comets that displayed anti-tails include Arend-Roland in 1957, Kohoutek in 1973, Hale-Bopp in 1997, Lulin in 2009, and Pan-STARRS in 2023. The anti-tail phenomenon is not unique to 3I Atlas, despite some claims. Astronomer Jason Wright at Penn State notes that comet C2014 UN271, Bernard and Nellie Bernstein, showed similar morphology in observations published by Farnham and colleagues in 2021. They interpreted it as slow ejection of relatively large dust particles predominantly from the sunlit hemisphere. The particles are too large for radiation pressure to blow away quickly, so they accumulate on the sunward side, before gradually spreading around the nucleus. This creates a sunward enhancement that looks unusual but follows from straightforward physics. Large particles, weak radiation pressure, slow ejection speeds. The combination produces an anti-tail. They formed 4.6 billion years ago from the primordial material of protoplanetary disks. Their composition reflects the conditions in the regions where they formed. Solar system comets that formed in the outer regions beyond Neptune contain more volatile ices like carbon monoxide and carbon dioxide. Comets that formed closer to the Sun contain more water ice. By analyzing the gases and dust in cometary tails, astronomers deduced the temperature and chemical environment of ancient protoplanetary disks. 3I Atlas, as an interstellar comet, provides a sample from a completely different stellar system. Its CO2-rich composition suggests it formed very far from its parent star. The tail composition tells us about ices that condensed from the disk around another star potentially millions or billions of years ago. The tail's behavior also affects how much material we lose from the comet during each passage near a star. Radiation pressure and solar wind constantly strip material from the nucleus. The comet shrinks with each orbit. For solar system comets on closed elliptical orbits, this means a finite lifetime. Eventually, all the ice sublimates and only a dead rocky nucleus remains, or the comet fragments completely. Jupiter family comets with orbital periods of a few years lose material rapidly and survive perhaps only tens of thousands of years. Long-period comets from the Oort cloud that visit the inner solar system only once every million years or more can survive many more orbits, because they spend most of their time frozen in the outer solar system. 3. I Atlas, on a hyperbolic trajectory, will make only this one pass through our solar system. After swinging around the Sun and passing Jupiter at 0.36 astronomical units on March 16, 2026, it will coast back out into interstellar space, eventually reaching the speed it had when it entered the solar system. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, expected to begin operations in 2026, will discover many more interstellar objects. Current estimates suggest LSST might find one or more interstellar comets or asteroids per year. Each discovery provides another data point about the population of objects drifting through the galaxy. Are they mostly comets or mostly asteroids? What compositions dominate? Do all interstellar comets show tails when heated by the sun, or are some so depleted of volatiles that they remain inactive? Does radiation pressure always shape their tails into the familiar configuration, or do unusual compositions produce unusual tail structures? 3. I Atlas is only the third confirmed interstellar object. The sample size is tiny. Statistical studies require dozens or hundreds of detections. The Japanese Aerospace Exploration Agency successfully demonstrated solar sail technology with the Icaros probe, launched in 2010. It unfurled a 14-meter square sail and used photon pressure from the sun to accelerate. No fuel required. Just a large reflective surface catching sunlight the way a boat's sail catches wind. The force is small but continuous. Over months and years, a solar sail can reach high velocities. Proposed missions to the outer solar system, or even to nearby stars, rely on solar sail or laser sail propulsion. Understanding exactly how radiation pressure acts on different materials helps engineers design more efficient sails. Comet tails are natural experiments in radiation pressure acting on irregular dust grains of various compositions and sizes. Observations of how comet tails develop provide real-world data for validating theoretical models. For low Earth orbit satellites, atmospheric drag dominates, but for geosynchronous satellites at 36,000 kilometers altitude or higher, radiation pressure becomes a significant perturbing force. Mission planners must account for it when calculating fuel requirements and orbital evolution. The same physics that makes comet tails point away from the sun makes satellites drift from their assigned positions. Both follow from photons carrying momentum. The discovery of radiation pressure had philosophical implications beyond the technical details. It demonstrated that light is not just a wave or just a particle, but exhibits properties of both depending on the experiment. The classical wave theory of light, developed by Christian Huygens, Thomas Young, and James Clerk Maxwell, successfully explained interference, diffraction, and polarization. But radiation pressure revealed that light also carries momentum, a particle property. Each photon has energy equal to Planck's constant times frequency. Each photon has momentum equal to that energy divided by the speed of light. When billions of photons hit a surface, they collectively exert a measurable force. This wave-particle duality became central to quantum mechanics in the early 20th century. Louis de Broglie proposed in 1924 that if light waves have particle properties, then particles might have wave properties. Erwin Schrödinger developed his wave equation in 1926. Werner Heisenberg formulated matrix mechanics. The quantum revolution followed from taking seriously the idea that waves and particles are not mutually exclusive categories. Kepler could not have predicted any of this when he observed the comet of 1607. He just noticed that tails point away from the sun and guessed that sunlight must be pushing them. Brilliant intuition. But it took 3 centuries to develop the physics and technology needed to measure the effect directly. Lebedev's experiment in 1900 used sensitive torsion balances in vacuum chambers to detect forces of millionths of a Newton. Nichols and Hull refined the technique. By the 1930s, physicists could measure radiation pressure precisely enough to test quantum predictions. Today, laser cooling and optical tweezers routinely use radiation pressure to manipulate individual atoms in cells. The techniques that won Nobel Prizes in physics in 1997, 2012, 2017, and 2018 all rely on understanding how photons transfer momentum to matter. After perihelion on October 29th, the comet moves away from the sun. The tail now leads the way, pointing ahead in the direction of travel. The nucleus follows its own tail through space like a bizarre reversal of how we imagined comets should move. But this is exactly what must happen when radiation pressure and solar wind push material away from the sun, regardless of orbital motion. When the comet approaches the sun, tail behind. When the comet recedes from the sun, tail in front. The tail always points away from the sun, always, without exception. This single fact, observed for centuries, contains within it the key to understanding how light interacts with matter, how the solar wind shapes the solar system, and how stars influence everything around them across vast distances. The comet will reach its closest approach to Earth on December 19, 2025, at 1.8 astronomical units distance, 169 million miles, no danger of impact. By March 26, it passes Jupiter at 0.36 AU. Then it coasts outward, past Saturn's orbit by 2030, past Uranus by 2040, past Neptune by 2050. By 2100, I-Atlas will be beyond the Kuiper Belt. By 2200, it enters the inner Oort cloud. By the year 3000, it leaves the sun's gravitational influence entirely and returns to interstellar space. For the next million or 10 million or 100 million years, it drifts through the galaxy, a frozen snowball carrying traces of its birth system and of its brief encounter with our sun. If it survives that long, many comets fragment during perihelion passage. The thermal stress cracks the nucleus. Gas pressure from sublimation in interior pockets blows sections apart. Comet 2, I-Borisov, showed signs of fragmentation in 2019. 3I, Atlas, might not make it to interstellar space intact. But for now, in late 2025, the comet obeys the same physics that governs every comet ever observed. Solar radiation heats the nucleus. Volatile ices sublimate. Gas streams away carrying dust. Photons transfer momentum to dust grains. Radiation pressure pushes small particles outward, forming a dust tail. Ultraviolet light ionizes gas molecules. The solar wind's magnetic field picks up the ions. Plasma streams along field lines, forming an ion tail. Both tails point away from the sun. The same mechanism Kepler intuited. The same forces Lebedev measured. The same physics Maxwell predicted. Universal principles applying equally to comets from our solar system and to visitors from other stars light years away. A recent paper published by Casey Lisa and colleagues in October 2025, analyzing 3I Atlas, notes something important. The 46-kilometer upper limit on nucleus diameter cited by some researchers is explicitly a reference point for a comet of the same brightness with no coma, not an actual measurement. The real upper limit from Hubble observations, as of August 20th, is 5.6 kilometers diameter. The nucleus could be as small as 440 meters across. This matters because some claimed 3I Atlas might be artificially large based on the 46-kilometer figure. Misrepresenting what papers actually say creates confusion. The comet's properties are unusual but not impossible for a natural object. High CO2 to water ratio, early activity beyond Jupiter's orbit, nickel without iron in the coma. These are anomalies worth studying. They tell us about formation conditions in other stellar systems. But they do not violate known physics. They do not require exotic explanations. Radiation pressure and solar wind still explain why the tail points away from the sun. That explanation worked for Halley's Comet in 1607. It works for 3I Atlas in 2025. It will work for every comet humanity ever discovers, because physics is universal. The same laws apply in the Oort cloud and in interstellar space and around distant stars. When 3I Atlas formed perhaps billions of years ago, orbiting a star whose name we do not know in a location we cannot pinpoint, it accumulated volatile ices in the cold outer regions of that system. Gravitational perturbations from a giant planet or a passing star kicked it onto an escape trajectory, For eons it drifted through the dark space between stars, frozen, inactive, invisible. By chance, its path intersected our solar system. As it fell inward past Jupiter's orbit, solar radiation began warming the surface. Carbon dioxide ice, with its lower sublimation temperature, vaporized first. Gas erupted from the nucleus. Dust followed. And immediately, radiation pressure took over. Photons from our sun pushed outward on dust grains that condensed around another star. The solar wind, carrying our sun's magnetic field, grabbed ionized molecules and swept them outward. The tail formed, pointing away from our sun, just as it would have pointed away from its home star if that star's radiation and wind affected it the same way. The mechanism cares nothing for origin, only for the strength of radiation, the size and composition of particles, and the speed and density of the stellar wind. On a clear night in southern Chile in October 2025, if you have access to a telescope with at least 8 inches of aperture and you know exactly where to point it, you can see 3, Atlas yourself, a faint smudge in Sagittarius, moving slowly against the background stars. You cannot see the tail with small telescopes. The tail is too faint. But professional instruments see it clearly. 56,000 kilometers long in August, 100,000 kilometers by September, perhaps longer by October as perihelion approaches. That tail, invisible to your eye but recorded by CCDs on mountaintop telescopes, points away from the sun, away from the source of heat and light and pressure, away because that is what physics demands. A force pushes, an object moves, momentum transfers, light pushes dust. Magnetic fields guide plasma. The result is inevitable, universal, true for every comet that ever was or ever will be. Lebedev and Nichols and Hull proved it in 1900 and 1901 with sensitive instruments in sealed chambers. Maxwell predicted it in 1862 from his equations of electromagnetism. Biermann, in the 1950s, connected it to the solar wind. Decades of spacecraft observations at multiple comets confirmed every detail. And now 3I Atlas, an interstellar visitor from a system we will never see, demonstrates once again that these principles hold everywhere. The comet's tail points away from the sun because photons carry momentum and transfer it when they strike matter. Because the sun emits a wind of charged particles that drapes magnetic fields around obstacles. Because physics is the same everywhere in the universe. The observation is simple. The tail points away. The explanation took centuries, but once understood, it unlocked understanding of light, of momentum, of electromagnetic interactions, of stellar winds, of how stars shape their environments across millions of kilometers. One phenomenon, countless implications, all encoded in the direction a comet's tail points when sunlight touches it. As 3, I Atlas recedes from the sun after perihelion in late 2025 and early 2026, the tail will gradually diminish. Less solar heating means less sublimation, less gas and dust streaming away. The coma will shrink, the tail will fade. By the time the comet passes Jupiter in March 2026, activity will decrease significantly. By the time it crosses Saturn's orbit a few years later, it will return to the frozen, inactive state it maintained during its long interstellar journey. The tail will vanish. Only the bare nucleus will remain, coasting outward toward the edge of the solar system and then beyond. But for a few months in 2025, this visitor from another star showed us that even objects born in alien stellar systems obey the same physical laws. Even an interstellar comet's tail points away from the sun. Universal physics, universal principles, no exceptions.